Hello everyone, welcome to the video tutorial for performing Principal Component Analysis or PCA in Sift. This tutorial will show you how to use the application to perform PCA using data from your workspaces. As a brief summary, PCA's application in biomechanics refers to the statistical technique used to reduce the dimensionality of large complex data sets, such as motion capture or kinematic data. It identifies the main patterns, or principal components, that explain the most variance in the data. This allows researchers or outside parties to focus on key movement patterns or biomechanical variables while filtering out noise or less significant variations. If you would like to indulge in a full treatment of waveform-based PCA to find differences in waveform data, see the explanation presented in the Research Methods in Biomechanics textbook. This is available at the link on the Has Motion Software Documentation wiki page, right here. For this tutorial, we will be comparing the knee flexion extension angles between participants with osteoarthritis and a normal control group. Our problem is to provide an explanation for differences in knee flexion extension angles between osteoarthritic walking versus normal walking. We can accomplish this by defining two groups that meet these definitions, performing a PCA on them, and interpreting the results. This tutorial uses overground walking data from roughly 100 subjects divided into two groups, normal control and osteoarthritis, which is moderate to severe. This dataset can be found in your Sift program files under the demo folder. I will be showing you how to find this dataset. As with previous tutorials, we start with an empty project in Sift where we begin by loading the workspaces and defining the queries relevant to our question. First, we click the Load Library option in the left toolbar to open the Load Library dialog. Then we can click Browse to select the folder where the data is stored. For the demo files, we can navigate to the local disk, then select Program Files, navigate to the Sift folder, and click on Demo. We can now click on Select Folder and Load in order to load this dataset into Sift. Now that we can close this dialog box, we can then navigate to the Explore page using the left toolbar and select the Query Builder icon to open the dialog. We will be manually creating two groups based on tags, one for subjects with osteoarthritis and one for normal subjects. We begin by defining a query for subjects with an OA tag which indicates osteoarthritis. To do this, first we can select the Add button in the Query section, name the query OA, and click Save. The condition name can also be OA. In the Signals tab, these are the characteristics. The type should be set to derived, the folder should be set to PCA, the signal name should be set to r_angle, and the component should be set to X. The Events tab can be skipped as there are no events in this dataset, as the signals are already sectioned into gate cycles. In the Refinements tab, we can check Refine Using Tag and select the OA tag and then hit Save. Next, we will define a query for subject with an NC tag which indicates normal control. In this case, we can easily modify our previous query rather than starting from scratch. Again, we can select the Add button in the Query section, name it NC, and click Save. We can also name the condition NC. The settings in the Signals tab will stay the same, as you can see here. However, in the Refinements tab, we can again click Refine Using Tag, and this time click the NC tag. Now we can hit Save on this too. Now we can verify that the new NC group has the same signal and event selections as the OA group. Now that we see the two queries in the query box, we can now click Calculate All Queries and close the dialog box. There will now be two groups in the Explore page sub-windows groups list. Selecting either of these will display the associated workspaces in the workspaces list below. We can verify the queries that we produce in the first section by visualizing our traces. First, we can make sure that the plot type is set to signal time. Then, select all groups and select all workspaces. Now we can check only the Plot Workspace Mean checkbox and click Refresh Plot. If the traces are not colored by group, the plot may not be as informative as we are looking for a comparison between the OA and NC groups rather than individual subjects. If this is the case, which it is, open the Show Data Options dialog from the application toolbar and select Group under the Display Styles From option here. We can also make sure that there is a significant enough color difference between the two groups by again selecting the data styles and then adjusting the color. We can adjust it so that we can see a significant enough difference between the two groups. Once this is done, inspecting the plot shows that although participants from the two groups walk very differently, obvious when watching them in person, their knee flexion angles are actually quite similar. Because the traces overlap significantly between the two groups throughout the entire gait cycle, conventional statistics will likely not be useful for describing the differences between these two groups. In order to find the key differences between the groups, we must do a more in-depth investigation. This is one of the motivations behind PCA. By transforming our original data into a coordinate system based on principal components, we will end up with a few dimensions that will explain most of the variance in the data set. This, in turn, will help us to explain and detect the differences between the groups. Now we can begin the main component of this video, performing the principal component analysis using the feature in Sift. The reason for running a PCA is to identify key movement variations, compare movement patterns, reduce dimensions for classification, and visualize group differences by looking at the entire waveforms and not just summary metrics. We can begin by ensuring that all groups and all workspaces are selected in the list, which they are. Then we can select the PCA icon on the upper toolbar, which will bring you to the analysis page and prompt the PCA settings dialog. We can set the name for this PCA, which will be PCA OA NC, representing the principal component analysis comparing the osteoarthritis and normal control group. We can set the number of PCs to 4, and this refers to the number of principal components you want to retain from the PCA. Each component represents a linear combination of the original variables that captures a portion of the overall variance of the data. Selecting 4 PCs means the software will focus on the 4 most significant movement patterns or biomechanical variables contributing to the differences between the groups. We can ensure that the use workspace mean is checked, and we can select Run PCA. The results of these calculations will automatically populate the PCA graphs on the Analyze page. As you can see, running the PCA prompts this dialog box to open showing information about the results. The results from the PCA are described in 6 windows: Variance Explained, Loading Vector, Workspace Scores, Group Scores, Extreme Plot, and PC Reconstruction. This tutorial will focus on 4 specific windows, which don't include Loading Vector and PC Reconstruction. However, full descriptions of each window can be found on the HasMotion wiki page. The first window we will go over is the Variance Explained window. This displays the variance by each principal component as well as the cumulative variance. It is important to verify that the calculated principal components explain a significant amount of the dataset's variability. In general practice, you want enough principal components to explain 95% of the dataset's variety. Otherwise, there will be at least a moderate amount of variation that your analysis has not captured. In this example, we can see that the 4 principal components explain 96% of the dataset's variability, which is sufficient. If less than 95% of the dataset's variance was explained, then we should rerun the analysis with more principal components. Left-clicking on a bar will display the exact variance explained by that specific component. Next, the Group Scores window helps us to determine if there is a significant difference between the groups for any individual principal component. To check this, we look at the mean score for each principal component and their standard errors. If the mean score along with its error range doesn't cross the x-axis, it means that there is a significant difference between the groups for that principal component. In this tutorial, we see that the principal components 1 and 2 show significant differences between the groups, so we will focus on these 2 PCs for the rest of the investigation. As with the Variance Explained window, hovering over a point will display a tooltip with precise values for that group score. Now that we've identified our principal components of interest, we can switch to the Workspace Scores window and plot PC1 versus PC2. In this plot, we're looking to see if the groups are clearly separated, and as we can see that there's a noticeable distinction between the groups in this 2D space. While PC1 captures more of the dataset's overall variability, PC2 helps better distinguish between the groups. Even though this isn't shown mathematically here, you can visually observe this separation. If we use both PC1 and PC2 together, we get an even stronger distinction between the groups, which is especially useful in further analysis. If you want to explore the original data linked to any specific workspace, we can click on a scatter point in the plot, like this outlier, and the corresponding data will be highlighted in the queried data plot on the Explore page. So we can navigate to the Explore page and see that this specific trace from the workspace is highlighted. In order to unselect, we can click Control H. The Extreme Plot widget helps us visualize the variation captured by each principal component. By selecting Mean and Slider from the drop-down for plot type, and selecting the PC number 1 from the drop-down for PC number, we can hit play and see an animation where the blue line varies within the range of the mean plus or minus 2 standard deviations of the principal component. We see that the green line stays static, representing the mean. For PC1, this variation shows an offset in data, likely due to things such as the difference in posture, and this may not be as relevant for answering our question. We can hit stop, and we can now switch to PC2 and play the animation. And the differences become more pronounced during the late stance and mid-swing, providing more meaningful insights into the data. This tool is useful for understanding how each PC contributes to movement variability. In conclusion, this tutorial on performing Principal Component Analysis, or PCA, using Sift has demonstrated the steps required to reduce the dimensionality of biomechanical data, identify key movement patterns, and explore variance within datasets. By following these steps, users can better understand complex biomechanics datasets and highlight critical features that contribute to variability in motion. This leads to more targeted and meaningful analysis. Thank you for watching.